Thank you very much for having me here. I'm very excited to speak at CodeMesh, and I was really happy when asked until I saw this tweet by Bodil yesterday, and then I got very sad because I too would have loved to see Simon speak, and unfortunately you're stuck with me, but we'll give it a good go.
He's coming on stage later today.
Excellent. All right. So. First of all, I'd like to describe myself as a commercial coder, which is someone who writes code for a living. And I'll do a quick survey now so I can sort of gauge the audience. How many of you would say that you're commercial programmers, industrial programmers? Oh, excellent. This talk is aimed at you. And what about academics in the room? 1, 2, maybe? I see. Well, that's less great because my background is in physics and I'm an industrial programmer, so unfortunately I'm going to fudge some things in this talk. They'll be, strictly speaking, not quite correct, but close enough, and I'm sorry for that in advance. So, as commercial coders, typically picture the scene. I've just got a job at a company called PetCorp. And PetCorp is a company which is revolutionizing the marketplace in adopting pets. So I'll give you an example. Oops. This is what the website looks like. Note the garish colors. Inspiring theme, and probably there's some crypto integration somewhere where you can play with, Dogecoin or something like that. And I've been tasked with writing a backend for this website. And it's quite simple. Essentially, what I want to do is write the backend for that search bar, which you see, which seems to be lifted from about 10 years ago. But anyway, I digress. So maybe the query will look something like this, right? So it's a post query, pets search, name is equal to Fido. And that's fine. And I knocked that up quite quickly. And it gets to a week later. And the front-end developers say, well, what we really need is to be able to search pets by age. That's okay, it's not too much of a problem. And I knock something up in the backend. I have a Fido and age equals 3, which searches for pets which are named Fido and 3 years old. And it gets to a week later in the sprint planning meeting. And we have to be able to do equalities on the ages. And then further, maybe my team lead says that we need more complex queries, and so on and so forth. And so on. And so at the end of the day, what I realized is, well, to be honest, I've written a language, right? So a quick show of hands, how familiar is this scenario to everyone here? It doesn't have to be in query strings, it can be in config. Yeah, this is pretty familiar. And I have a confession to make. I've done this at least 3 times in 3 different languages. And those are warts which my coworkers will have to live with, and not me, fortunately. But a few years back, I started to wonder, if this is so common, surely we can learn from it. Maybe there's like a name for it or something like that, which we can use as case studies. And it turns out that this is so common that, of course, there's a rule for it. And this is the rule. Any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of common Lisp. And it's made me really sad because this rule is really negative, right? And I thought, well, there's actually not too much wrong with this. It's not too much. There's a few negative words, but we can change those, right? Because we're good developers. So I propose that we have a new rule, which is that any sufficiently complicated insert commercial language here program contains an formally specified bug-free implementation of half of common Lisp. And this is where my talk begins. Thank you very much. So, final confession. I'm going to be using a commercial language, which in my case is Scala. I tried to do it in Java, but unfortunately it wouldn't fit on the slides properly. I have done it in Java before, and I'm very sorry for that. So, all right, so quick primer on Scala. At the top is our notation for products, and at the bottom is our notation for pattern matching. That's really all we need to know, and also a quick primer on Lisp. This is Lisp syntax. So we have our function application, f, applied to x and y, and at the bottom we have what looks like a predicate, which is whether the pet's name is Fido. So we have equa here, name, pet, Fido. And the first thing that we need to do when we write a language is we need to create a syntax tree, right? And that's pretty simple, because we've got a simple language that we want to make. So this is our syntax tree. We have our sealed trait expression. We have our literals, which can be numbers or strings. We have our symbols, which are pet in this case, or anything that we want to take. And we have function application. And at the bottom is an example of a predicate which we might have, right? So our symbol is equa, which is our equality operator. Function application, the name, which is another accessor on pet, and if the name is Fido. This is great. Well, not really, because to be honest, we really want to run this. So we need to go about writing an evaluator. And because I'm a commercial coder and a physicist, I do stuff in quite an ad hoc way. So I'm just going to do it via trial and error. All right? So let's start writing it. So we have a function apply. We don't know what we return, so we have to return an A. And the first two cases write themselves. In the case that we have literals, numbers or strings, we simply unwrap the value that we contain, right? So if our string was foo, then we'd return foo in our evaluator. It's pretty simple. But what about symbols? And what about function application? Well, in the symbol case, what we're trying to do is we're trying to look up something inside a context, right? So what we want to do is we want to introduce that idea. So this is our context. It's a map, really, from symbol to any, because we don't really know what it is. And it can fail because it doesn't have to be inside the context. And here's an example of a context for plus. X robot plus, x is a double, and y is a double, and we return the function x plus y. So that's fine. What about function application? Well, remember Greenspun's rules from before. Like a sufficiently complicated program contains a subset of common Lisp. Well, Scala is also a sufficiently complex program, and therefore also contains a subset of common Lisp. And therefore, we can just use that for function application, right? So this is case apply. And so we have our function application here. We've got our symbol, which we must look up, and we have our arguments. In case that it's 1, we just do a function application using Scala itself. In case that there's 2 arguments, then we do the same thing. This is great. So I'm just going to go with a demo here. Can you guys see it? Excellent. Right, I'm hoping this works. Christ, it doesn't work. Give me a sec. Why do I have dependencies? I don't need that. Oops.
It's maximized again.
Yeah, there we go. So we import domain. What?
Is that your dependency?
No, thankfully it's not. It's because I'm in here. Yeah, that's really annoying. It's in a sub-project. What did I do? Oh. Cool. Finally. Right. For some reason, this takes a bit of time sometimes. Okay, so let's create an expr this time. So we have our parser, and let's just do 1 + 1. And because it could fail, I think we want to go on. Whoops. Yeah. And then we do eval, e, and what was it again? I think it was head dot default context, I think. No. I should have just called it E. Excellent. So we can see that we have returned the result. And we're all done, right? Like, this is the end of the talk. No, not quite. So let's say that a week goes by later on, and our CEO introduces a new pet, a new animal, introduces fish. Okay? And so far we've been trying to filter on, how many legs an animal has, and I'd like really not to get into the philosophical arguments of whether fish have legs or not. But it might look something like this. Oops. So these are our dog, cats, and our fish. And you notice that fish don't have legs, right? We don't really think that they should have legs. And in our function to get the legs of the actual fish itself here, we notice that it's incomplete because we can't write that particular implementation. So something's clearly wrong here, right? If we run that program, it will blow up. So what we really need is a type system. And I think of the type system as a set of rules which constrain the programs which can be written. And our type system is what I'd call too permissive. It allows programs which are incorrect to be written. Okay? So let's do this again through trial and error, and let's introduce what we think a typer should be. And so this is my interface to the typer. It's only one function. It takes an expression, and it returns either a string of expression or a type. And the string expression is basically the error case. Okay? Again, and our goal, of course, is to reject this particular program, because it should not be able to be run, right? Because essentially, fish can't have legs, we can't write that program, and it shouldn't be run. So let's just write down which types we already have in our type system. We have numbers, we have strings, we have booleans, and we have functions. It's pretty interesting. And functions have arguments, which are types, and they have a return type. And so the simplest type system that we can write, based on that, is pretty similar to our evaluator. In the case that we find an expression inside our tree, which is a literal, we simply return the literal type. What about symbols and function application? Symbol case is exactly the same. We create a context, and we look up the symbol inside the context, and if we find it, then we just return that type. Otherwise, we throw an error. But function application is a bit more interesting. So what we're going to do is we're going to introduce a new rule, right? And the rule is going to be quite simple and very intuitive. A function needs to be applied to arguments of the correct type and length. And this is rule number 1 in our type system. Okay? So if f is a function which goes from a to b to c, and then x must be of type a, and y must be of type b, and the resultant expression is going to be of type c. It's pretty simple. But hang on a minute. What type is paired? So far, we haven't defined anything, really, for paired. So the answer every time that you find a problem when designing a type system is to just introduce some more rules, make it more expressive. So we're going to introduce the idea of record types, which essentially allows us to get these dog, cats, and fishes. And we're going to introduce coproducts. The idea a type can be one of multiple types, a set of types. I'm going to introduce a new rule that a type A is considered a subtype of B if A is equal to B, or if B is a set of types, then A is within that set of types, or if A is a subset of all the types inside B, in the case that they're both coproducts. And so we revise our first rule. A function now can be applied to arguments not only of a particular type, but a subtype as well. But then we have a few other complications too, right? Like, well, let's say that I introduce if statements. What should that return? And so I introduced the dual of the coproduct, which is product types as well, which are unions. So again, we list out some rules in plain language. So if A and B are not coproducts, then the union of A and B is A union B. If A does not equal B, otherwise we just add them together if they're already unions. So in an if statement, if one branch returns us one type and the other branch returns us the other type, then the resultant type is a union of both of them together. It's pretty intuitive. But let's get back to our original problem. So originally, we had this predicate. We had the symbol less than, number 3, legs, and we had pet. But if pet can be all the animals which I support, what type should it be? Sorry, what type should legs be, right? Well, there's two issues. If I allow it to be all animals, right, so dog to cat, just set all animals to int, then it's too permissive again. We have the same problem that we had before. But in the latter case, if I only allow dog and cat, and my pet is a set of all animals, then obviously, I've got no real way of writing this program in the correct way. And so that's the opposite side. Rather than being too permissive, we're too restrictive now. Again, we have to make our type system more expressive. So we're going to brainstorm, right? We're going to come up with an idea. We're going to say, let's imagine this particular construct, an is construct. And I'd like it to look something like this. I'd like to ask our program if the pet is a fish. And if it is a fish, I'd like to be able to do things that fish can only do. And if it's not a fish, then I'd like to do things that fish can't do, right? Pretty simple. And on the runtime level, this is pretty simple because I can just do a check. But what about at the compile time? So my ideal behavior is that in this branch, pet should be inferred to be a fish. And in the else branch, pet should be anything but a fish. And like inside the Boolean conditional, if I do stuff like not and or, I'd like it to reflect it in the branches. So for example, if I do not fish, I'd like the branches to be reversed. So what we're going to do is we're going to abstract a little bit to try and understand our problem a little bit more. So this is our form, our expression, if you like. So what should go into A? Well, if we think about it, in our type system so far, everything has a type. So as long as it's a valid expression, anything can go into A. And what should go into B? Well, B can only be a type, really, right? And not only can B only be a type, but we'd ideally like to reject programs where we're checking on something which is impossible. Like, we don't want to be able to say, is pet a string, when we clearly know it can't be a string, because it's not inside its set of types that it's possible to be. So we'll introduce this idea of a context from before, but then what we'll need to do in each of the individual branches is to change the context. And we'll introduce the idea of a bound. Okay? And what you'll notice is two things. One is that I've changed the context now, rather than taking in an expert of symbol, just to take in a general expert. And the second, that the bound looks really similar to a context. Because it is really similar. Because in the case that I'm on one branch of my if statement, I simply overwrite the values in my bound. Right? So for all the expressions inside the context, I overwrite them. Because I know that inside that branch, it's going to be of that particular type. But what about in the other side? So let's say that we have a symbol x. And x is of the set of types of foo, bar, and baz. So from what we've said before, is x foo should return the bound that x is equal to foo in one of our branches. What should this be? Well, the thing is that in our outer context, we already know that x is going to be constrained, right? So what we really want to say is that we want to minus all the types that it can be inside that branch with the types which it can be on the outer context, which we call the complement. Okay? So in the outer context, x can be a foo, bar, baz, and the not bound should return that x is of type bar and baz. And in the case that x can't be anything, then we've probably written the program wrong. So our if statement is going to be a little bit different now. So if now takes an A, which is of type Boolean, and B, which also returns a bound. And in one branch, it applies B, and in the other branch, it applies the complement of B. So we can finally type check this program. All right, so if the pet is a fish, we return 1.0. Otherwise, we return legs of the pet. Because we know that it's not a fish anymore. So let's hope this works. So what's our thing? Oh, I can't see, obviously, now. What was it? So there was an if statement, right? And it was the pet was a fish. Otherwise, legs of a pet. That was correct? Yeah, that looks fine. And then, sorry. Yeah, there we go. So what we're going to do is we're just going to run the typer on our expr, and I think it was new pet or typer context. And voila, it gives us number correctly. And then let's do the reverse case. Well, we just want the legs of the pet. Well, we haven't actually reduced what it can be. And boom, it fails. Excellent. OK, so we managed to do it. So just to give a quick recap, we created an abstract syntax tree, then created an evaluator, and we created a simple type system. And we made it more expressive as we were playing around with the rules which we wanted it to obey. In general, if there are two things that I'd like you to take away from this talk is, one, type systems are pretty simple. The amount of code which was written for this type system was, give or take, about 200 lines of Scala code. It's really simple and easy to play with evaluators. I think it was about 10 lines of code or so. And you can do some really cool things, like you can write your own compilers, etc. And what I'd like to do is to encourage all of you to go forth and write some more languages, hopefully now slightly more formalized. And as it says, please go forth and scheme. Thank you very much.
We've got all the time for questions if you've got any. The type systems in the early morning, I could see why we're very excited formulating questions. That's one.
Yeah, thank you very much. At the start, you thought about, or you talked about what language you'd like to use for this talk. Have you ever thought about doing this in Lisp?
In Lisp itself?
Yes.
Yes, I have. So I mean, as you can probably see from my IDE, I'm a proud Emacs user. I have used Scala and different variants of Lisp inside, and I think they're fantastic. I really like using them. But at the same time, I've yet to find, at least in the area which I work, Lisp tends to be quite hard to use, and so I have to deal with some other languages sometimes. Also, Lisp is untyped, and I don't like that. Most Lisps.
All right.